All right, so let's take a look at section 7.5. Okay, so we've talked about some basic identities so far. Let me go back. Okay, last test we did the reciprocal identities, tangent and cotangent, and Pythagorean. Okay, we're going to look at a couple more sets of identities, starting off with sum and difference. Okay, so I wanted you to take a look at these two expressions, sine of x plus 3, where the plus 3 is in the parentheses, and then almost like you've done a distributive property with sine, sine of x plus sine of 3. Okay. Anybody think these two things are going to be the same, or are they going to be different? What do you think? Just take a guess. About Alex, what do you think?
It's
Not the same? Okay. So you're thinking that you can't just take the word sine and distribute it out?
Yeah.
Yeah, you are right. They are different. Okay, and one way to look at it is in terms of transformations. When you add or subtract a number inside parentheses, that's a horizontal shift. In this case, it's a horizontal shift, 3 units left. This is sine of x plus sine of 3 is a number. So it's kind of like taking, just adding a number onto the end. That's a vertical shift. Okay? So these are different transformations. Okay? So they won't come out the same if you graph them. Okay, let's take a quick look. Okay, that's a small section of it graphed. I kind of zoomed in because you haven't shifted it much. Okay, you've only shifted it like up 3 units, which in terms of my window, okay, now, you know, depending on, well, if you look at x, let's say you shifted that 3 units. Look at my window. My window is negative 123 to positive 123. You're not going to see a shift of 3 that easily, unless you zoom in. Okay, so that's what I tried to do a little bit. Okay, zoom in. And we can see they're not the same. Right? If you look at the table, some values you pick will come out the same, like 0. Happens to come out the same in both, just a coincidence. Pick something other than 0, like 1.2, 1.3. They come out close, 0.074, 0.075, but they're different. Okay, so that's the point. They're not the same picture. So you can't do a distributive property with that. Okay, so we're going to start out with 4 basic formulas. This is called the sine of a sum. We're going to look at sine of a difference. We're going to do cosine of a sum and cosine of a difference. The tangent ones, I'll write them down, but we're not going to do a lot with them. Let's start out with the cosine of a difference. Okay, so similar idea as the first example I gave you, except instead of sine, let's start with cosine. So you cannot distribute the word cosine. That'd be nice if it worked that way, but it doesn't. Okay, it turns out that the cosine of a difference is this. So the cosine of alpha and beta would be 2 angles, 2 numbers. Take the cosine of the first angle times the cosine of the second, plus the sine of the first angle times the sine of the second. Now, it's not bad to just remember this one, but all 4 of the formulas that I'm going to give you, they all look like this. Sometimes it's a plus, sometimes it's a minus. They're too similar to really keep straight easily. So you can make a reference sheet with these and use that on the test. The proof of it's on page 409. It's a pretty lengthy proof. Okay, it'll probably take about 20 minutes, 15 minutes to go through it. So we're not going to go through it because I don't think the value from doing it is worth the time we need to invest doing it. It starts out with this diagram. You do not need to draw that because we're gonna hold off on the proof. Does everyone have the formula above it? Okay, so that's called the cosine difference identity or cosine difference formula. Okay, and we can use it to perform calculations. And the goal is to use the cosine difference formula, and you want to rewrite the number 15. Okay, try to rewrite it using angles that we know how to work with. Okay, we've talked about special angles before when we did unit circle trig. Anybody, because like for example, you could do 20 minus 5, but 20, that's not an easy angle we know how to work with, and neither is 5. Okay, how could you rewrite this, James?
45 minus 3.
Right. Okay, to do this, you want to pick numbers that are multiples of 45 and 30. So 45, 90, 135, 180, 225, 270, 315. And then 30, there's some overlap with that. 30, 60, 90, 120, 150, 180, 210, things like that. Any of those angles, if we type them in on a calculator, you're going to get a number or a decimal you should recognize. Okay. Any question on that step? Now just use your formula. Let alpha be 45, let beta be 30, and fill it in. Cosine 45, cosine 30. And it's kind of weird, but you got to remember when you're doing the cosine difference formula, it actually uses a sum when you write it out. Okay, it's just the way it is. And then it's the sine of 45 times the sine of 30. Each one of those is going to be an answer we should recognize. If you don't have them memorized which one is which, we can use a calculator, type it in, get the decimal, and then hopefully we recognize it from there. Okay, the cosine of 45 is 0.707. Anybody recognize what fraction 0.707 should be? Joe?
Square root 2 over 2.
Yeah, let's just square root 2 over 2. Okay, let's check cosine 30. That's 0.866. Anybody recognize what 0.866 should be? Let's get another square root. How about Darren?
Square root of 3 over 2.
Good. Okay, we could go back and use unit circle trig and derive this from scratch, but we're going to have to do it 4 times. It's going to take 10 minutes to do. All right, so if you have these values memorized or you can recognize them, that's good. Okay, sine of 45, it's 0.707. Again, we just got that one. And the sine of 30, that is 1/2. Okay, so do out your arithmetic and see what we get. Okay, Brianna, what's the square root of 2 times the square root of 3? Well, you're multiplying, so 6, yeah. Square root of 2 times square root of 3 is square root of 6. And then 2 times 2 is 4. But look in the other fraction. Denominator is also 2 times 2. So both of these fractions are going to have a denominator of 4. And Darren, what's square root of 2 times 1? Square root of 2. That's the exact answer for the cosine of 15. Okay, what's nice about this? It's very easy to check. Take 15. The cosine is 0.9659. Let's type this in and see if we get the same thing. Square root of 6 plus square root of 2. Divide by 4. 0.9659. Okay, so when I ask you for an exact value, this is the kind of stuff I'm looking for. Any question on that? All right, so what the cosine difference and the cosine sum and the sine difference and sine sum, what they really allow us to do is find the exact trig functions of any angle that's a multiple of 15. So we said before, you could do the multiples of 30 and 45. Well, really, we could do all the multiples of 15, which covers everything I just said. Okay? Because all your multiples of 30 are also multiples of 15, and same with multiples of 45. Right, so we could do angles like 15, 30, 45, 60, 75, 90, 105, 120, okay, things like that. try this one. Okay, so this one says to verify that the cosine of pi over 2 minus theta is the same as sine theta. If you were looking at it in terms of a transformation, you might write it like this. And kind of doing it that way, we're trying to prove that a horizontal shift to the left, followed by a reflection over the y-axis of the cosine function, somehow gives us the sine function. Okay, so that's what we're trying to prove. Okay, so on the left, we have a cosine difference. Okay, so we're going to do out our formula. Let that be alpha. Let that be beta. Okay, and let's see what we get. So it's the cosine of each angle plus the sine of each angle. Cosine pi over 2, cosine theta, plus, and now the sine of each angle. Sine pi over 2, sine theta. Now if I want to check and I don't remember, I could draw the unit circle diagram even faster. I could just use my calculator. I'm going to do it in degrees. Pi over 2. Jill, what's pi over 2 in degrees? 90. So let's take the cosine of 90. We get 0. So 0 times the cosine of theta. And the sine of 90. Anybody remember what that one is? So 90 degrees, sine looks like this. That's the 90-degree mark right there. So what's the sine of 90? Oh, Cody?
1.
Yeah, it's where sine hits its highest point. Okay, 1. Or just check on your calculator. Okay, Andy, what's going to happen in this first part? 0 times cosine theta. Yeah, this whole part becomes 0 and it disappears. And all you're left with is 1 times sine. Which 1 times sine is just sine. So we just proved that the cosine of pi over 2 minus theta is the same as the sine. In a sense, we proved a transformation. We proved it. Any question on that? Okay, if I gave you this one, anybody have a question, or does anybody want me to go through that one? Everyone feel like they could do something like that on a test? Basically, that's your first angle, that's your second angle. So it's cosine pi, cosine theta, sine pi, sine theta. And you do it out, and you might get a 0, something cancels. Got to get a negative somewhere because the final answer has a negative. But any question on how you do that? Okay. So if you have a chance, try that one on your own because there will be some like that on the test, but it's very similar to example 2a. Okay. And pi is the same as 180 if you want to type it in degrees and check it. All right, so that's cosine difference. We're going to show where the cosine sum comes from. Okay, this actually isn't hard to show since we already know the difference formula. We just have to keep these two facts in mind. Sometimes these are called even-odd identities. Okay, I didn't teach you these separate, but it turns out if you take the cosine of a negative angle and then the cosine of the positive angle, it's the same thing. Take cosine of 20, 0.94. Take the cosine of negative 20. It's still 0.94. Comes out the same. With sine, it's a little different. If you take the sine of a negative angle, you can take the negative and put it in front. You can't just get rid of it like you can with cosine. But it's basically like you could take the negative and put it in front. Okay, so keep those two identities in mind. To figure out the cosine sum formula, I want to use the cosine difference formula. So my question is, how can you rewrite alpha plus beta as subtraction? What do you think? How can you do that? It's like if I said to you, I want you to take 3 plus 2 and write it with subtraction instead. So think about what kind of signs you'd have to use. James?
Alpha minus negative beta.
Yeah, alpha minus negative beta. Look what you just did. Okay, you just made it into a cosine difference. That's the first thing we're going to plug in. That's the second thing we're going to plug in. Let's plug it into the cosine difference and then see what happens. I think both of these situations are going to come up. Right, so we're going to get, remember, cosine of each angle plus sine of each angle. So, cosine alpha, cosine negative beta, plus, and then sine of each angle. Sine alpha, sine negative beta. Now the sine alpha in the second part and the cosine alpha in the first part, can't really do much with it. It's just these negatives, which we'll use the identities up above. So we get cosine alpha. Cole, what does cosine negative beta simplify to?
Cosine beta.
Yeah, you can just, with cosine, you just get rid of the negative. Okay, it just goes away. So far, this kind of looks just like the formula for a difference. Let's see what happens here. Plus sine alpha. What about sine negative beta? We can't just get rid of the negative. But Kobe, what can I do with the negative?
Put it on the line.
Yeah, we can kind of put it in front so it becomes a negative. Well, instead of just putting it in front of this one, why don't we put it in front of the whole thing? So what ends up happening is because this negative comes out, just like it did right there, it makes this whole second part a negative. Okay. So it's sine of alpha, sine beta, but the negative goes out in front. Okay. This is your cosine sum formula. Cosine of each angle minus sine of each angle. The only thing that's different is the plus became a minus. That's it. Okay? Any question on that? So let's use it to figure out, everyone have the formula? You know what, let's write out how you would set this up, but I actually want to do a different angle. But you know, yeah, we'll just do it. We'll do the other angle I'm thinking of later on. It's just this is kind of similar to what we did before. You'll see why in a second. How can you rewrite 75 degrees using angles that are multiples of 30 and 45? And don't overthink it too much. James?
30 plus 45.
Yeah, 30 plus 45. It's the same two angles we just used before. So we're going to get an answer that looks very similar to what we had. Okay, so it's cosine each angle. Now with the cosine sum formula, when I write it out, how about Kelsey? What symbol do I use, plus or minus? Yeah, cosine sum uses a minus, just the way it works. Sine of 30, sine 45. And we already should recognize every one of those. Okay, cosine of 30, that's your root 3 over 2. Cosine of 45 is root 2 over 2. Sine of 30 is a half. Sine 45 is root 2 over 2. So my common denominator, how about, Emily, what's my common denominator here? 4. Yeah. It's 2 times 2 in the first fraction, 2 times 2 in the second. Square root 3 times square root 2, square root 6. And 1 times square root 2 is square root 2. It's very similar to the first problem. Questions on that? Yeah, I just want you to see if you can figure out how you would rewrite this. Cosine 105. You've got to rewrite it using angles that are multiples of 30 and 45. And there might be more than one way to do it. There is more than one way to do it. Anybody see how you, yep.
60 plus 45.
Good. That's one way to do it. 60, that's an angle that's easy to work with. So is 45. Add them together, you get 105. You could also do it as a difference. Before I write it, does anybody see the way to do it as a difference? So the angle that you'd have to start out with, that's a multiple of 45, is 135 and 30. Okay, 135, that's just your 45, 45, 90 triangle in quadrant 2. So you're going to get some negatives when you take cosines of that. Okay, but you could do this problem either way, and you should get the same answer. Any questions on how we wrote that? Now, you can't do it for every angle. Okay, if I said to you to find the cosine of 17 degrees, you can't. There's no way to split up 17 the way we need it. Okay, but you can do any number that's a multiple of 15. All right, let's look at our sine sum formula. This will probably be the last one that we derive. And then from here, I'm just going to give you formulas. We proved this earlier. Sine of theta equals cosine of pi over 2 minus theta. Let me go back to it. Sine, you're right here. Sine of theta equals cosine of pi over 2 minus theta. We proved that. Right, so we know that's true. So this fact allows me to take something that's a sine of something and rewrite it as the cosine. Well, if I can rewrite this as cosine, and I already have a formula for cosine of a difference, then I can figure out what sine of a sum is. We're going to rewrite it. Okay, and the way you rewrite it is basically just substitute in what your angle is and write it as cosine pi over 2 minus, just put whatever your angle is. In this case, that's our angle, alpha plus beta. Right? So we're going to rewrite this using the identity up above it. Right. Can somebody tell me what I'll have inside parentheses? Rewrite this, instead of using theta, just use the angle we have now. What's in this box? Yep.
So it would be pi over 2 minus theta?
Yes, and since you're subtracting alpha plus beta, I put it in parentheses because you're subtracting the entire angle. Whatever that angle is, you're subtracting. Okay, and what I'll do is distribute out that negative and regroup it a little bit. So it's cosine of, let's write it like this. Pi over 2 minus alpha. Okay, think of that as a group. And then we also have to distribute it out to beta. Now we have cosine of a difference. That's the first thing. That's the second thing. Plug all of that into your cosine of a difference formula and watch what happens. So we're going to have cosine of each angle plus sine of each angle. Cosine of my first angle. Cosine of my second. Plus, now do sine of each angle. Sine of my first. Sine of my second. Okay, focus on this first part. Cosine of pi over 2 minus an angle. What is that the same as? Cosine of pi over 2 minus an angle. This is really something else. Yeah? Yeah, sine of, what's my angle in this case? Alpha. Anytime you take the cosine of 90 minus an angle, it's the same as just doing the sine. We proved that. So I just used that identity right there. The second part, just keep it the same. Now this part we didn't prove, we could have proved it. But does anybody have a guess what the sine of pi over 2 minus alpha is the same as? Using the kind of reasoning we did up above. Any guess what it might be the same as? So if cosine of pi over 2 minus alpha was the same as sine, what would we hope that sine of pi over 2 minus alpha is the same as? Priya? Okay, so cosine, let me do it in degrees. Cosine of 90 minus an angle is the same as sine. So if there was the same kind of relationship, sine of 90 minus an angle, we would hope is the same as cosine. It is. Okay, it does work out the same. We could do the whole proof of this, just like we did if we wanted. It turns out sine of pi over 2 minus alpha is the same as cosine. So that's cosine times sine. This is your formula for the sine of a sum. Okay. It's sine of the first angle times cosine of the second, plus cosine of the first angle times sine of the second angle. Now they're getting a little trickier to remember. But when you have sine of a sum, it does use a sum. It's not cosine with cosine and sine with sine. It's one of each. Okay, and the sign difference is pretty much the same thing, except change plus to a minus. So sine of the difference, sine of the first, cosine of the second, minus cosine of the first, sine of the second. It's kind of tricky to remember. Those are the four most important identities we're going to do today. The sines, cosines, sums, and differences. Okay, any question on that? Okay, so hopefully you can see very clearly you can never just distribute the word sine. That doesn't work. It's a little bit more complicated than that. Right, so with the sine sum and difference, we can do the same kinds of things. You can find sine 15, sine 75, sine 105, anything like that. Okay, let's just let's try this one. Okay, 165, that is it is a multiple of 15. If you weren't sure, you could always check. It's 15 times 11. So there is a way to do this. Anybody give me a way to split up 165? You could do it as a sum, or you could do it as a difference. But the trick is you got to give me two numbers that are multiples of 30 and 45. Yeah?
135 and 30.
135 and 30. Yeah. That'll work. I was also thinking of, oh no, my way wouldn't have worked. Yeah, that'll work. But you could probably do it other ways too. Okay, 135 plus 30. Now let's do it out quick. Okay. Sine of a sum. Sine of the first, cosine of the second. Plus cosine of the first, sine of the second. Right, you're gonna get nice answers, well, special answers for every one of those. So sine of 135, that's 0.707. Cosine of 30, that's your root 3 over 2. Cosine 135, negative 0.707, so that's negative root 2 over 2. And sine of 30 is 1/2. So you finish it up, you do all that out, you're going to get square root of 6 minus square root 2 over 4. The square root of 6 and square root of 2 come up a lot because you're combining square root 2's and square root 3's. Okay, so there's the basic idea. And again, what's nice is you can check it. Type that in, type the original problem in, see if it comes out the same. Okay, the tangent and sum and difference, we're not going to use them as much. In fact, for now, I'm just going to give you the formulas. But you could do the same types of things we've been doing. You could find tangent 75. You could find tangent 105, things like that. It's a little messier. But the tangent of a sum is the tangent of the first angle plus the tangent of the second, divided by 1 minus the product of the tangents. Okay, and the other formula for a tangent of a difference is tangent of the first minus tangent of the second, divided by 1 plus the product of the tangents. So I think we can all see a symmetry to these. Basically, you're just changing pluses to minuses to get one from the other. But you do not have to prove those. I might just give you a problem in the homework where you have to use it. So it just barely comes down to arithmetic and simplifying arithmetic. That's all it comes down to. Okay. Any questions on those two? All right. So the next part we're going to look at, instead of adding inside the argument, let's multiply. Right? So just from a standpoint of transformations, I hope everyone could recognize these cannot be the same. The one on the left, that's a horizontal compression by a factor of 2. The one on the right is a vertical stretch. Talking about two different things. They're not the same. It'd be nice if they were, because we're going to have a lot of problems with the argument, we wish it was an x, but instead it's like a 2x or a 3x. Probably won't get any higher than 3x. Otherwise, these problems start to get really, really time-consuming. Okay, but the goal is we got to come up with some identities that can change arguments that have 2x into arguments that just have x. I want to verify this. Turns out this is an identity. I'm going to put it in a list of 3 of them, or 5 of them or so in a second. But I want to verify that this is true. Sine 2 theta. It's kind of like a trig identity from the test. Okay? Except this wouldn't have been one you would have known how to do before. I want to take 2 theta, and I want to rewrite it. My hint to this is rewrite it using a sum. How can you rewrite 2 theta as a sum of 2 separate angles? It'd be like in algebra if I said to you, okay, I got a final answer of 2x. What did I combine together? What 2 things would you combine together to get 2x? How about Colton? Like, pretend I said, I want you to make up an Algebra 1 test. I want the answer to number 2 to be 2x. You make up a problem so the answer comes out to 2x, and you add 2 things together. What 2 things could you add together and get that as the answer? X plus x. So we'll do the same idea here. What 2 things could you add together to get 2 theta? Theta plus theta. Good. Now, Andy, what do we have on the right-hand side now? This is a what? Something special we studied today. There's a name for this. Just look at the expression. What's the trig function?
Sine.
And what are you doing? What is this?
Added.
Okay, yeah, what's another name for adding? What's the answer that you get when you add 2 things?
Sum.
Sum. This is the sine of a sum formula. Okay, sine sum formula. So we just did that right here. This was your sine of a sum formula. Okay, let's take sine of the first, cosine of the second. So let's do it out. This is my first, this is my second. Oh, they're the same. So sine of the first, cosine of the second, plus cosine of the first, sine of the second. Again, they're the same. Cosine of the first, sine of the second. So I have sine times cosine plus cosine times sine. Okay, Darren, if you compared sine times cosine to cosine times sine, what would happen if you switch the order you multiply in? It's the same thing. So think of this. This is sine times cosine. This really, you could write this way if you wanted to switch the order. Sine times cosine plus sine times cosine. James, how many sine times cosines do we have? 2. Sine times cosine. So we just proved that sine of 2 theta is the same as 2 sine theta cosine theta. We're not going to prove the other identities. Okay, so for sine 2 theta, it's the same as 2 sine cosine. That one's nice because you only have one choice. When you have cosine of a double angle, 2 theta, you have 3 choices. You could write it that way. It's cosine squared minus sine squared. And using the Pythagorean identity, you might think it looks like this. What I just wrote here and what I have up above are not the same. Sine squared plus cosine squared equals 1. That's something else. But you could use this to get that. If you did a substitution using this Pythagorean identity and wrote cosine squared as 1 minus sine squared, if you plugged 1 minus sine squared in for cosine squared and simplified, you'd get the second version. Likewise, if you solved it for sine squared, sine squared is 1 minus cosine squared. If you plugged this in for sine squared, you could get the third version. So they're all really the same thing, just rewritten a little bit. But it uses the Pythagorean identity I taught you last week. Okay, so most of the time, in fact, for algebraic problems, I'm going to have you stick with problems that involve sine and cosine. Tangent, it gets a little messier. You can do it. It's just not as clean of a problem. But here is the formula. So if you had tangent 2 theta, it's 2 tangent theta divided by 1 minus tangent squared. Right, so something you could do for like a calculation with this is, let's say that I had you find tangent of, I don't know, let's say 150. Or, you know, let's do something simple, 120. Okay, but for some reason, you just couldn't remember the tangent of 120. Well, if you can think of it in terms of tangent of 60, and you know that for some reason, but you don't know 120, you could figure this out. Because you could write it as 2 times the tangent of 60 over 1 minus the tangent of 60 squared. Okay? So if you're working with an angle, and you don't know that angle, but you happen to know half of it, and you know how to work with that, you could use these kind of formulas. Honestly, though, I don't know why you'd know the tangent of 60, but you don't know 120. Because they're very related. So, right? But you could do stuff like that with it. Okay, so let's take this problem, and I just want to rewrite it with sines and cosines. So in other words, when I'm done, I don't want any arguments here to have a 2 next to the x. The arguments can only be x's. Jill, if we look at the first part, 2 cosine x. Is there a 2 in the argument for that one? No. There's the 2 on the outside, but that's fine. We just don't want a 2 next to the x, and there isn't. So the first one is actually fine. We can leave that part. The second part, we have to fix it. Sine 2x. Okay, so using my identities from the previous page, who can tell me how to rewrite sine 2x? And I want it rewritten so it just has x. Okay, you can say other things, but if you give me a trig function, it cannot have a 2x in it. Yeah?
2 sine x cosine x.
Good. 2 sine x, cosine x. She just substituted in that identity. Okay. Now, Kelsey, what do these both have in common?
Cosine x.
Yep, they both have cosine x. Anything else? Give you a hint at what I'm going to do.
2.
They both have a 2 in common. Since we're adding two things and they both have something in common, we can factor it out. Okay, Kobe, if I factor out 2 cosine x from here, what am I left with? 1. If I factor out the 2 and the cosine x from the second part, I'm left with sine x. So you just took an expression that had a 2 in the argument. Now all my arguments are just x's. I don't have 2's anymore. Okay, any question on that? And that's it. Technically, they didn't tell us to factor it, but it looks a little neater, so that's why I did it. All right, so there's 3 more identities I'm going to give you. These are double angle. Well, we also have half angle. We have half theta, and half theta. I'm going to save those identities for the end. Okay, I'll give them to you. We're not going to do a lot with them. Okay, I do want to practice one more problem that ties in a lot of skills we've worked on. Okay, this is going to tie in quadratic equations. It's also going to tie in which trig functions are positive in which quadrants. Okay, so this one's, it's got a lot happening in it. So it is a time-consuming problem. All right, before you can solve this, okay, I basically want you to figure out the answer to that. What is x? Those arguments can't have 2's and 3's. We have to rewrite them so that they just have x's. Okay, let's start with sine 2x. Alex, how can I rewrite sine 2x? And you only have one choice for this one.
Sine x plus cosine x.
Okay. I heard, so 2 sine x. What did you say after that?
What? I mean, minus cosine x. No. Just times cosine x.
Times cosine x. Good. There's a lot of stuff to keep all straight. All right, so the first part is good for now. Cosine 3x. We don't have a triple angle formula. We could find one. We could look one up somewhere, but we don't have one. Okay? So what I want to do is rewrite 3x as a sum. And I want to rewrite it as a sum of 2 other numbers, or 2 other expressions. Okay. What 2 things can you combine together to get 3x? Yeah. 2x and x. Now I have a cosine of a sum. I'm going to go back. I'm going to look up my cosine sum. Actually, it's cosine, cosine minus sine, sine. That's the formula. And we're going to rewrite this. Keep the first part the same for now. We've got 2 sine x cosine x plus, again, if you're not sure, you just want to make sure you do the formula right. You can look it up. It's cosine of each angle. Cosine 2x cosine x. Oh, sorry, that's times. And then with the cosine of a sum, it uses the minus sine of each angle. Sine of 2x, sine of x. Okay, so it looks like it started to get a little more complicated, but at least now I don't have any arguments here that are higher than 2's. Before I had a 3, now I have a 2. Oh. cosine 2x. Actually, you know what? We're going to use, I don't think we're going to use that one. We're going to use the second one. This is the tricky part, how you know which identity to use. It's just this one is a little faster. So that's your cosine of a double angle. And then we have this, sine of a double angle. So we're going to use each of those. At this point, it's going to make it as complicated looking as it's going to get, and then some things are going to start to kind of combine, and we'll get like terms. All right. First part, keep it the same. 2 sine x, cosine x. Second part, change it to what I just circled. Cosine of a double angle is 1 minus 2 sine squared. So plus 1 minus 2 sine squared. This cosine x on the end, it's just going to stay the same. It actually, in a minute, it's going to be distributed out. But I won't do that at this step. Minus. Now for sine 2x, that one's pretty easy to remember. That's 2 sine cosine. I have to rewrite this. 2 sine cosine. And now if we're clever, we can do something else at the same time right here. Instead of writing 2 sine cosine sine, how can I put the two signs together? What would happen when you multiply sine times sine? It would be 2 sine x cosine x times another sine x. Priya?
Sine squared.
Yeah, this part is going to just become sine squared. It's kind of like if I told you to write 2 times a times something different times something else you already had. Well, instead of writing it that way, why don't you just do it that way? That's what we just did right here. Okay. So now, this part, I think it's good. Why don't we just distribute it out, and then you'll see something you can do. We'll do it separate, though. So 2 sine cosine. This part's just staying the same the whole time. This part's not changing. Plus cosine x. And I don't really like to distribute this because I'm going to end up factoring it back out in the next step. But I think if I don't do this, you're going to get confused if I do this step in my head. So I'll distribute it out. Minus 2 sine squared times cosine. Just multiply cosine out to each term. Keep the last term the same, and I think you'll notice something now. 2 sine squared cosine. Look at the last 2 terms. 2 sine squared cosine minus 2 sine squared cosine. Those are like terms. Anybody tell me what you'd get if you combine them together? Minus 2 sine squared cosine minus another 2 sine squared cosine is minus how much? James?
Minus 4 sine
Yeah.
squared 2 cosine.
Say it again. Think of it as minus 2 times something minus 2 times something. All you really get is minus 4 of whatever the something is. Okay, so everything stays the same, sine squared cosine, except minus 2 is just minus 4. I think you had changed something else there. But think of it like that. Minus 2 box is minus 4 box. Fill in box, okay, whatever the box is. Okay. Everything else stays the same. And now it's kind of going to start to get a little smaller. So minus 2 is minus 4. Now I want you to look carefully at each part and see if all three parts have something in common. And if it does, we're going to do something with that, and then this problem is going to start to look like something, I hope. Yeah? Right. You can pull cosine out of all of those. And watch what happens when you do that. You're going to be left with 2 sine x, a plus 1, which is why I said I didn't really want to distribute the cosine out just to factor it back out again, but I think people would have got confused if I didn't do that. And factor it out from the last part. Now, I think what I would do to make this a little easier to recognize what I'm hoping you recognize, put minus 4 sine squared x first. Put 2 sine x second. Put the plus 1 on the end. Anybody recognize what this really is right here? Minus 4 sine squared plus 2 sine plus 1. What kind of equation is that really? Yeah? This is really a quadratic equation. A is negative 4, B is 2, C is 1. Except it's a quadratic where you're not solving for x, you're solving for sine x. Okay? All right, so now we've done all the manipulating you have to do to this. Okay? Now we can solve it, which that was the question. Find the roots. Well, the first part we want to find when cosine x equals 0. Why? Because you're multiplying two things together and you're getting 0. The rule for that is as long as one of them is 0, 0 times anything will be 0. Okay? So there's two values that make cosine x 0. The way I think of it, I think of the picture. That's the picture of cosine. Crosses the x-axis in 2 spots. This first spot is pi over 2, which I'm going to write as a decimal. So 1.57. The second spot, this is 0, pi over 2, pi, 3 pi over 2. That's the second spot. 4.71. Those are the two values you can plug into the first part to make cosine 0. Now we've got to figure out the values of x that make the quadratic 0. Let's put these off to the side. So those are two answers. Okay, in this part, treat it like a quadratic. A is negative 4, B is 2, C is 1. Now do your quadratic formula. Just remember when you're done, it's not x equals, it's sine x equals. Okay, so we get negative b. Okay, this part we'll go through quickly. Plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, it turns out if you simplify that whole thing, you're going to get 1 plus or minus the square root of 5 over 4. That's what sine x equals. I'll leave all the simplifying and multiplying, I'll leave that for you. Right, so now we know sine of x. How do I know I'm solving for sine x? Look at the quadratic. Look at what's in the middle. It's sine. It's not just an x, it's a sine x. And let's round it off. Okay, we get two answers, 1 plus the root of 5 and 1 minus the root of 5, both over 4. So it's 1 plus the square root of 5 over 4. We get 0.809. So sine of x equals 809. And sine of x also equals 1 minus the square root of 5 over 4. Negative 0.309. Okay, now my last step to get x by itself. How do we get rid of sine? Darren? Inverse sine. So take the inverse sine of each side. Again, these are all approximate. We rounded. That's fine. Take the inverse sine of 0.809. And, oh, I was using radians. Sorry. So type in the same thing, just put it in radians. Inverse sine 0.809. 0.942. Now, here's the part where I have to remember there's 2 quadrants where sine is positive. Quadrant 1, which I just got an answer in, 0.942, and quadrant 2. Does anybody remember, what do you do with your reference angle to get an answer in quadrant 2? We subtract it from something. Subtract it from 180, or if we're doing radians, subtract it from, what's the same as 180? Yeah, pi. So 3.14 minus 0.942. So you get 2.192. Well, I think the book rounded it to 2.2. Okay, and the last 2 answers. Take the inverse sine of negative 0.309. We get negative 0.314. And now there's 2 quadrants where sine is negative. Quadrants, so we can see it, that's negative 0.314. Quadrants 4 and 3. Negative 0.3, that's an answer in quadrant 3. 4, sorry, that's quadrant 4. Okay, so to get our answer in quadrant 4, okay, what I'm going to do is take, or quadrant 3, take that negative 0.314, and I'm going to add it. You might say add it to 180, but you want to add it to pi, because we're doing this in radians. So take pi and add 0.314. 3.4, let's go 3.456. Okay, and I wrote the answers the book got. Let's just make sure we get the right one. So 0.94, we got that one. 1.57, we got that one. 2.2, yep, we got that. The book rounded the last one to 3.46, that's fine. 4.71, we got that. And 5.97. Well, we got negative 0.314. I would accept both. Okay, all the book decided to do was take and basically add 360 or add 2 pi. You can always add or subtract 360 or 2 pi to an angle to make it positive or make it negative. But I would accept the 4 that we have circled. That's fine. Okay, so that's a tough problem. There's a lot happening there. Okay, it's definitely the hardest problem we're doing today. It's actually our last problem. Okay, so the last slide is 3 formulas, which I'm not going to do an example with right now, but just so you have them. Okay, if you don't want to take them down now, you can get them on page 417. And they're half-angle formulas. Okay, so it's like the idea of double an angle, except it gives you a way that if your angle was cut in half, to write a formula where the angle is not cut in half. So it kind of gets rid of the dividing the angle by 2. It's not a very clean formula. It's a square root of 1 plus your cosine of your angle divided by 2. So what something like this would do, this would actually give you another way to find, let's say I asked you to find cosine of $15. And you said, you know what, I know there's a way to do it using the sum and difference, which it would be 45 minus 30. Let's say you didn't remember that formula. Well, if you remember this one instead, you could find the cosine of 15 by doing 1 plus the cosine of 30 divided by 2, and then take the square root of it. There's a different way to find the cosine of 15, if you didn't remember the way I taught you at the beginning of class. Again, thinking of 15 as, I didn't write this step. Think of it as 30 divided by 2. $30 divided by 2 is 15. Okay. Same thing with sine. And the last one is tangent. If you wanted to get rid of dividing by 2, it's the sine of the angle over 1 plus cosine. Okay, in a college level class, you'd probably go through and prove all of these and where they come from. Even you'd do proofs with them, like we did in the last section. But we're not going to do that. Okay, so that's an overview of the sum and difference formulas for sine and cosine. Those are the most important ones I want you to focus on. Okay. The next most important ones are the half angle ones, especially just the sine and cosine, double angle. And don't worry as much about the half angle. Okay. Focus more on the double angle and the other first 4. All right, so the homework is on 417. It's 1 through 5, 9 through 11. And then it skips around a little bit. So 17 and 18, 29 and 31A. There's more than one part to 31. Don't do all the parts. Just 31A. 37, 41, and 45. Okay, so we'll take a look at that tomorrow.